First of all, thank you, Parth, for letting us use this space for the second time. So, for the first time when we had was 1.5 years ago, and at that time as well, we were like amazed by the space Microsoft provides for community building and doing these sort of events. So, we are happy to be back again after 1.5 years, and hopefully, maybe after a year or so, we'll have another event here. And looking forward to that as well. So for this event, we were focusing on what is trending, and so that is why we are focusing on geospatial AI. This AI wave is now transpiring into like being soaked by the AI folks as well. So this event is all about that. So before we begin, I think I'll just give a brief about this community. There are a lot of folks who are yet to come. I think they'll come join in another half an hour or so. Even the speaker is a little bit late. But anyhow, I'll just give a brief about what this community is about. So this community was started back in mid of 2022, and it has been around 2 years now. That will be completing. So we've had over 16 events so thus far. These not just meetups of this kind, but also workshops, hackathons, and we've collaborated with different communities. Say IEEE GRS's Bangalore section. There's another community called OpenStreetMap community, which happens, they also conduct mapathons and hackathons. So that community, we've collaborated and done mapathons as well. So these are the kind of events that we've done. And if you can see on the map, so these are the places we've gone. This was last updated October 2023. From there on, we have not updated, but there are many more places that we have to add. We have traveled all across Bangalore and across multiple venues. I can see Microsoft Reactor is one of them, one of the early meetups that we had in the picture. So if you want to join, this community is now thriving. Geospatial is just starting to take its space, and there's a lot of exciting things that is happening, as you'll see and hear from the speakers. But if you want to join, we are live on all these platforms. Slack is where generally we discuss if there is job openings, if there are resources, or if there is some exciting news that is happening, we discuss there. LinkedIn and X is where we put our updates. Website is all the talks that have happened, and if you want to link back or see the GitHub repos. So we also have a GitHub repo where all the speakers, everything is open source here. All the speakers, whatever they present, the source code and the presentations are available on the GitHub, which you can you can access that from the website. So today we'll have 3 talks. One is from Rupesh, who is yet to come, and Koushik will be speaking on field delineation for farm boundaries, and third is Sumesh, who will be speaking on multimodal vector search. So I think before we start, I just want to show you guys the website, and then I think we'll move on to the presentations. So you can type Let's Talk Spatial, or just go to letstalkspatial.in, and here you'll find all our updates. So just last year we partnered with IEEE GRSS and organized a huge conference, which was one of the best conferences that happened for geospatial community. And we were partnering with them. So all the talks that we have had, as you can see, we have had 4 talks since October, but we're not updated. But if you want to see all our events, you can actually go there and click. So this one was from Microsoft Reactor when we had in 2022 October so there we had OpenStreetMap as our channel. So you can go through and browse this. If you are interested to speak, or just give us a topic where we want to organize events, or give us a place to organize event, or if you want to talk something related to geospatial, feel free to reach us. And so this is the team. I am Aman. So I work at Galaxy Space. There is Thiaku, who is at Satyukt Analytics. Amrut is IHS Senior Associate, and Santosh, who is now in Riyadh. So our team also is now started. We also want to grow the team, so if you are also interested, please reach out to us. So that is from my side. I think now I'll introduce the first speaker. So I'll just open up his slides and just a minute. Cool. I think that is all. So now I welcome Koushik. So Koushik is working at Spatial as Geospatial analyst. I think we have the first speaker as well. We can. Do you want to go ahead first, Rupesh?
Yeah, I can.
Sure. So sorry, Koushik. I think we'll go with the flow itself. So the flow was decided based on the level of, detail that we want to go in. First, we'll introduce what geospatial AI is. Then we'll go to field boundary delineation, and then third, we'll go to vector search, which is quite new. So this will be the flow. Now, before I begin, now I'll introduce Rupesh. So Rupesh is the lead engineer at Skyser, which is an edge computing platform or company which is working on edge computing things. And so Rupesh has 5 years of experience in geospatial domain alone. And so he's actually building, he was the lead developer for SkyServe's Storm platform, which is deployed on edge now. And so he's tackled very important challenges, which is developing geolocation methods for reliable device positioning without GPS, and also geocoding algorithms for route planning, location matching, and identifying nearby points of interest. So I think I'll hand over this stage to Rupesh. Do you have can you share the slides, or you want to?
I can connect also. Or
Because the recording is happening here.
okay. I'll just share the slide. But I'm not sure. Okay, I will export as PPT.
Yeah. उसको बोल दो, उनको बोल दो और एक नाम रख दो. हाँ. So sorry guys for the delay, but so we usually start at 10:30 only. Even if we say it is at 10, we start at 10:30.
Just sharing.
Sure.
I'll share you on WhatsApp.
Yeah.
I would like to just quickly check whether it's working.
Sure.
It's coming. Few more seconds.
And also we are live, so I'll just I've shared the YouTube link, or if you search it online on the platforms, you can share it across to those who have not been able to join.
Yep.
67 MB.
Lots of images. Are you opening in Lavelle? Okay.
Right?
Just go here. I need to check if this is working. Can you play it? Just one last one. Can you play this one? Just. Go to the next one.
Just close this. Start this.
Go to the first slide.
Yeah.
All right. Am I audible? Okay. Good morning, everyone. And so sorry for the delay. Even though I spent quite few years on geo routing and geocoding, I think map still doesn't work the way it should. So yeah, before I start, I would like to know how many of you are from geospatial domain itself or are totally aware of it. Okay, more than half, actually all. So maybe many of the use cases that I will show you are already something that you might be aware of, but I wanted to start just in case there are folks who are from non-geospatial domain, and also from the folks who have raised hand, how many of you write your own AI models? Okay, less than half. All right. So let's start. So today's topic, which I am covering, is artificial intelligence for Earth observation. So Earth observation, I'll come to each of these topics. I made the slides in a manner that it can be beginner friendly for the folks who are from non-geospatial domain as well. Since we have many of the folks from geospatial domains, I'll quickly go and recap what it is all about. So what exactly is Earth observation? So basically, Earth observation in technical terms is defined as the process of acquiring data for the Earth's surface and atmosphere. All right. And there are various data capture methods that are used to get this data, and everything has its own limitations and plus point. So basically, if you look at the drone technology that came, it serves as a very good high resolution images, which are very useful for even minute details and resolution as low as 3 centimeter, 5 centimeter. But the problem is drones can't fly all day long or can't cover the entire globes at once. And on the other hand, you have satellites which can cover the entire globe in 1 day time, or if you have a constellation, it can just cover entire day with the help of constellation in 1 hour, 2 or 3 hours. So basically, with the level of different technologies that you use, you have some trade-offs that you will lose some accuracy or resolution when you're working on satellite data. That it would not be as precise, as clear and crisp from the drone, but you have the plus point of covering the entire Earth, which is technically not feasible from the drone. So many of you might have already know, but yeah, we have two types. So our topic would be mostly covered on the satellite data, how it's captured and how it's used in today's geospatial world. So on the satellite part, there are two types of satellites. One are called passive sensors and one is active. So passive sensors are those which actually don't emit their own radiation, but collect the radiation that is reflected from Earth's surface or atmosphere. And the source of this radiation is, of course, the other sources, but primarily sun. So whatever radiation is coming, it gets reflected, these sensors collect, and based on that they produce an image, which is then downlinked to the ground stations that are connected across the globe. So, but as you might see, since the source of radiation is sun, it is dependent on the day and night cycle. That means you can't image on night, and obviously you can't image through the clouds as well, and that poses certain challenges because many of the use cases which I will also cover, you require them to cover during the cloudy days or during the rainy days and during nights as well. On the passive sensors, usually what we are aware of is the visible spectrum, that is red, green, blue, the optical image. Your phone, my phone and everyone's phone usually covers this range, and we are used to it. But satellites, on the other hand, can cover a wide range of electromagnetic spectrum, and this allows us for many other use cases, which I will cover later on. So one of the use cases I'm just broadly showing is, this is a false color image which is made using the NIR band, which is called near infrared band. So you combine near infrared with the red and green component, you get this image, and every image that is composed of these different bands has certain significance based on what you have based on how it's made. So for this false color image, it actually helps you identify the vegetation and the health of it based on how much chlorophyll is present, which reflects the NIR band range. Moving on to the active sensors. Active sensors, as I said, they have their own source energy, which is used for illumination. So basically they send the signals themselves, the radiation, and then capture it back. Not much like sonar, but you can consider it in the same technology range, where you send the signal, you capture and analyze the signal that is received, and based on that you make the measurements and come up with a new image. One such active sensor, I will cover only one such active sensor image, which is SAR. So SAR emits electromagnetic pulses, and that gets detected by the antennas on the satellite, and based on the intensity of the return pulses you can make the image. And the major plus point is you can always image during day and night cycle, even during the night, and also through the clouds, which makes them one of the excellent use cases for defense use cases, where you want to continuously monitor a place and for surveillance purposes. So some of the parameters related to Earth observation, I think once again, as you all are from Geospatial, you might already know, but yeah, I'll just quickly cover. So one is spatial resolution. It determines how much basically spatial resolution determines how much in the ground, how much each pixel in the image corresponds to the actual distance on the ground. So what it means is, higher the spatial resolution, which is measured on the ground sample distance, GSD. So basically it is the distance between center to center of 2 pixels in the image, and it will tell you each pixel in the image corresponds to how much distance in the real world scenario. Much like if you see maps, if there are in many of the maps, it is written map not to be scaled. That means you can't measure 1 centimeter is 100 kilometer, but you will see some defense based maps which are written for scale itself. That means 1 centimeter on that map will tell you, okay, this is actual 10 kilometers in actual part. So defense guys always use that, and you can actually determine how much distance it is there. On the similar concept you have for the image as well, that for based on the spatial resolution, suppose it is 3 meter, then means 1 pixel to another pixel, 1 pixel covers 3 meter. And what is the significance of this? So significance is, higher the I will go higher by the higher number directly. So basically 10 meter, 20 meter, that means you can detect only objects greater than 20 meters. That is also very difficult, but yeah. So lower the spatial resolution, the more number of objects you can detect from the satellite itself. Then there is scene size. Scene size is basically every image you capture will always have a height, width, and the exact area that it can cover. On satellite terms, it is called as swath width, which determines the length of the strip that it captures in one single go. So basically scene size determines that how much of the area you can cover in a one single image, and it is inversely proportional to spatial resolution. That means lower the number of spatial resolution means higher the detail, like 3 meter, 1 meter, the scene size would be smaller, like you can cover only 15 square kilometer in one go or 20 square kilometer. But the higher the number you go in spatial resolution, like 100 meters, 200 meters, you can cover as big areas 200 square kilometers in one go. Just for reference, if anyone wants to see that, Bangalore's area is 740 square kilometer around. So for such satellites, even that will take 2-3 passes to actually cover the entire Bangalore area. Then there is revisit time. So as you know, satellites revolve around the Earth, and it will just keep on rotating, revolving around the Earth. That means it will see one area after some time only, and that is defined as revisit time. That after how many hours or days will the satellite see the same location again. And this is one of the very crucial aspect in Earth observation terms, because it determines what are the use cases you can target. Suppose you are on a defense basis and you want to monitor something each day, but your satellite revolves and sees the same location after 15 days, then that means this is not useful. But on the other hand, if you are monitoring crop which might not grow as much in 15 days, this could be a useful factor. And then there are some image quality related factors. I will just go quickly. So bit depth, how many image processing experts here? Anyone? Okay. So bit depth determines how many I will say nuisances or each pixel. So basically, okay, I'll just tone it down. So each pixel is represented in bits, and what you can do is it goes in the power of 2. So basically a bit depth determines how many color ranges you can determine on each pixel. So in usual sense, you have a bit depth of 8 for most of the images, even our normal images. So that becomes 256 colors, 2 to the power 8. That means the red, green or any blue color you have will give the range of 0 to 256. Higher the bit depth, more colors you can record. Just like how in TVs are there, higher the like 2 to the power 12 if you go, you can record 4096 distinct colors, and higher, even if you go 16, you can record even higher. What this will allow you is to distinguish very light or very dark regions. So basically you can differentiate between shades of gray also when you go for higher bit depth. But with a lower bit depth, all gray will look like most likely same or close to black. And that is the profit of having higher bit depth. But actually that increases the size of the image, so that has to be taken into account. Then off nadir angle is, by default satellites have cameras and sensor systems, and it revolves around the earth and it takes photo. But rarely it takes photo directly by seeing on top of it. So basically you have a camera and there is an earth, but if it looks at certain angle and captures this photo, then that means it has taken the photo in certain angle. That means your resultant photo will have some tilt towards it. And when it comes to the providers and it comes to the end users, the geospatial folks also who are using this, many of the times this will always be corrected in most scenarios. But in some scenarios you will have to correct it if you're directly dealing with the operator side. Basically the satellite guys, if they are directly selling you the data without correcting this, then you will have to account for that tilt and then correct the image to make it rectangular, not skewed. And then there is sun elevation angle. So basically when the earth is here, the satellite is there, but sun is also that side. So basically its sun elevation angle tells you that what was the sun's position when you captured in photo or in image, and that determines how long the shadows will be casted. And this is one of the crucial steps in geospatial that based on use cases you might have to consider this. Suppose you are trying to image some areas, hilly areas where there are a lot of trees, usually high trees. So if you get a photo or an image with a lower sun elevation angle, that means the sun was here or something, then most of the things below the trees will not be visible, because that will be casted by the shadows, and that image will be good for nothing. You will not be able to use that image for any kind of processing stuff, because all you will see is shadows of the trees. And basic is cloud cover. So cloud cover is basically, as you can see, Bangalore is cloudy today, so it determines how much cloud percentage is there in the image, and that determines how much useful area you have depending on what kind of sensors you are using to capture the image. Okay, lots of theory. I guess we'll start with some use cases. So I will cover 7 different use cases. Many of these use cases can be achieved using statistical algorithms. By statistical I mean the band maths. So the geospatial folks already know that there are different bands, and you can have different mathematics behind the bands, like use NIR and RED to compute an indices which have some different meanings. On the other hand, if you are not interested directly on band maths, you can also train models using different algorithms like SVM, support vector machine, random forest, and other CNN based architecture algorithms as well. So I will cover the use cases broadly, and in the one of the last slide I will also go to a more technical approach where I've mentioned where each of these use cases fall under the AI part and what are the common models, AI models that are used for that purpose. So first one is water body monitoring. So this is one of the burning issues for the government and climate activists and everyone around the world, that you want to monitor your water bodies. By monitor, it doesn't mean that you're just checking whether water bodies exist or not, but also different parameters about the water bodies, whether how is the water quality health over there, which can be determined by algae. So if your water body has a lot of algae and the civic body is pumping water out of it and distributing it to the folks, the normal folks for drinking purposes, then that might not be healthy. And in such cases, it is required that you detect in earliest way possible, and you and you make sure that you do proper treatments. So using Earth observation data, what we can compute is different indices. One such index could be either NDVI, which is the vegetation index, or the moisture vegetation index, or the moisture index, to tell whether how much water content is there on the ground level. And based on that, you can determine not just this, but there is other indices as well, like chlorophyll indices there, NDCI, it's called NDCI, and that you can use to compute whether the pixel value. So basically, each pixel value will determine you how much of that content is there. So it moves towards green, that means vegetation, not necessarily vegetation, but at least water is not there. If you're calculating moisture or something, then that means on the lower scale you go, at least moisture is not there, it is confirmed, but green is not exactly equivalent to green cover or vegetation. So it depends on the band mass or the algorithm that you use to determine it. And so basically these legends are nothing but crafted for human purposes, and across different websites you will see different fancy legends that are being used. Some are usually constant across standards across the industry, but some folks have changed their meaning, but you will always see some numbers or something over there to determine what it means. So this is one of my hometowns river. So usually this photo was taken from last year actually. So the river is usually there, but it dries up or during the summers. So what it happens is the river is there, and then suddenly one patch of the river has dried up over there. And when it dries up, what folks do is it has basically you have a river bed. So many of the folks for the time being also cultivate something over there. And that can be represented on that can be viewed on the images as well. So the next use case is agriculture. So AI in precision agriculture. So IoT has boomed a lot in agriculture, and the reason for that was most of the folks wanted AI level precisions in agriculture. That is to determine what is my crop health, what is the soil moisture level that is currently there. What is the effectiveness of the fertilization, and if you are over irrigating the crops, or if you are putting more chemicals than required. But the problem with the IoT sensors is the scale. If you have 100 square kilometer land, there are not enough number of IoT devices you can put. You can always put, but it's not sustainable because the financial implications will grow 10-fold, 100-folds. So the better alternative is using the satellite images. So you capture the satellite image of the area, and based on that you can determine various methods and parameters that can help you determine the health of the farm. So this is one such application that there is one such application theory I'm showing you. So suppose there is a farmland over there, you can determine, you can capture an image, and based on the several indexes, so here it's written NDVI, NDMI. So NDVI will capture the vegetation part, that how much vegetation is there, but NDMI will capture the moisture level in the soil. Okay, so that can determine that whether irrigation is proper or not, and NDVI will help you determine what is the current crop status, like whether it's near to the harvest or not. And obviously in this one you can use different other bands of the sensors to even determine the crop type. So there is a study, how many have you worked or heard about hyperspectral data? Okay, so many of you. So in hyperspectral there are various bands that can be used. So basically for the other folks I'll tell. So hyperspectral bands are nothing but, just I mentioned there is visible spectrum, near infrared and shortwave infrared red. But in case of hyperspectral you can cover a wide range of frequency. And each frequency, so scientists have studied for each frequency how does a certain crop react. So basically you throw that frequency range on that crop, and the reflectance of that radiation is different for different crops. So you will have you have enough research papers, some of them I have mentioned in the resource. So there are resources which tells you, okay, if you throw this this frequency band to this agriculture part and the reflectance is in this range, then that means the crop is wheat. If it is beyond this, then it is rice, and so on and so forth. So using that you can also determine the crop type. And obviously since you determine how many crops or vegetation is part of there, you can also estimate the yield. That is based on prediction, obviously. That okay, this much crop yields this much, so this much should yield this much. And then the third use case, this again is very important one, is land monitoring. So in case of land monitoring or land cover mapping, the objective is to determine how the land use, basically, in other words, land use. So how the lands are being used for different purposes and how can you accurately determine it. And the image segmentation is a crucial part which determines how to segment this. Basically, you give an image and then apply image segmentation algorithms on top of it, and that will help you determine by noticing the patterns on each pixels. You can determine the adjacent pixels whether it's related to that or not. And since I mentioned each pixel will have different values, so you can have values from 0 to 256 and for different bands as well, red, green and blue. So if you feed this into a CNN kind of model, it will come up with an algorithm. So basically CNN models are very good with mathematics. So I'm telling you there is a matrix of 2 by 100 by 100 or something, and you have 3 layers on it. So one for red, another matrix for green band, another for red, green and blue, and each matrix value has certain values in it, a number between 0 to 256. Now you feed everything into a convolutional neural network, CNN models or other different types of models, and what it will try to do is determine a pattern between these kinds. So basically for vegetation part, it will see okay, if I have pixel values of this, then this means that it is closely related to vegetation. Obviously you need to put training data in such a manner that you put it okay, these are the vegetation. You put the annotated data first, train your model, and then give the new image, and it will try to identify based on the patterns it recognized on the previous one. With that in constraint, so this is one of the actual outputs. So if you see the satellite image and the semantic classes that it identified on the image, and it very well actually identifies. So there is road, then there is water, then there is vegetation, building and land. And some of you might think what was the other alternative that people were doing before it. I've personally seen folks were actually in the very earlier days, they were actually annotating it manually. So basically there will be a person sitting with a GIS software and they would be annotating where is road, where is vegetation, where is building. And as you can see, that is a tedious job and it takes a lot of time to process. So even if you process area like Bangalore, it will take a lot of time for 1 person, 2 person or 10 persons to actually segment this. But with the use of AI, you can segment everything in just like 1 hour, 2 hours, 3 hours. So that is the one benefit you have of using AI versus the other things. And I'll just show some of the other models output that I personally made or I've seen. So what is the importance of urban change detection? So many of the government are actually pursuing this field very aggressively because there are a lot of illegal constructions happening around around every place, basically not just India but everywhere. So in urban change detection, what you do is you take a photo of an earlier time and you take a photo of the next time, and then you compare these images. Now if you compare it visually, you might not see much differences. Obviously major differences one can see, but there are very slight differences that are there. But with the help of this need not be purely AI, you can use image processing algorithms and compare the differences between these two images, and you will see wherever these white blocks are there, these are the new additions to it, or at least changes happened from the previous one. And now what kind of change is there, again you can give another model to determine whether something has been added, removed, or what kind of stuff has been added. And this will help the basically urban planners and other folks to determine whether something, suppose this area was an illegal or government zone where construction should not have happened, with such as like national parks or something, and then you can easily identify and tell them to the respective folks or organizations. And this is one of the models. So if you see first, second image, then third image is the hotspot area where it is showing where the changes were detected, and the fourth one is a basically time series of that entire prediction, and the image. So fourth one is a prediction as well as the time series of the changes. So where the buildings were present and not present or demolished, etc., etc. This is one again from it's around Meerut railway station. As you can see, the in the normalized NDVI, some green patches are changing regularly. This need not be case of deforestation because forest can change due to seasons and other temporary constructions as well. So the green cover might change accordingly. So even with the geospatial technologies that we have, even if you can predict some, you can get a number, the actual result might still be interpreted differently based on the other scenarios that are present. Fifth one is road network detection or road network mapping. So this is one of the, even I have, so as Aman mentioned, my previous work was based on geocoding and geolocation. So I was actually working on stuff to make maps as in Google Maps kind of stuff, where we were importing large hundreds, thousands of GBs of data and putting it in a server with much bigger RAM of 300 GB, 400 GB, generating the road maps. So these maps are not generated automatically, you will have to generate. These maps are called tiles in normal sense, and what you do is you put the data of every road network that you have, and it generates in the conventional sense, it generates that data. But using satellite mapping, you can also do mapping for places where you don't have road network data, because road network data comes after you have already established a road. So this is for already established roads, and this is what Google does. This is what one of my previous company was doing. So we have the road network data, we import it, then you run a bunch of algorithms on top of it to make the road maps, and that is how you see what it is there on Google. Google is not using directly this, obviously, because it's very risky. As you can see, predicted are not exactly accurate 100%, but these are very useful in cases where you want to monitor some new road networks that are being developed or some new constructions that are happening. So there you can see the road networks, and based on this model it can automate. So the model is called road network segmentation or identification. You can search on Google as well. So this was part of the Deep Globe challenge, extracting road surfaces from satellite imagery. So even though it looks simple, when you train the model, you can see the noises around it do affect the road networks detected, and that is why the predicted and ground truth is still different. So the ground truth, you have the exact roads, and when most of the time someone has went there and surveyed and put a ground truth map. Predicted is very close to it, but still not very close. So we need improvements on this area, and that can greatly enhance the road network mapping and the way we are developing right now road network technologies and routing technologies. But what if you can use, so this is one of the use cases I was thinking ki, okay, you can get the road network, but if you can make Google like maps or directly automatically. So Google like maps are not made directly, as I mentioned. Once you make those tiles, someone has to put the styling layer also, and that also has to be coded. And there you code ki how buildings will look like, how water will look like, what color water would be, what color roads would be, what color highways would be, and all those things you see on Google are actually determined by someone who has written those logics and rules. But using GAN models, what you can do is you can take an image, and then with training on lots of visual data on satellite original data, like maybe OpenStreetMap data or Google Maps. Officially you can't train on Google Maps legally, but yeah, you can still train. Then on OpenStreetMaps, so what you can do is you can actually generate the color related images as well. So you can see the generated images are very close to the original maps that are there, and this has very good result on that part. And this if the service is good enough, you can actually make use of this to actually make a real-time routing based application where it can generate maps on real time, not just, so Google Maps are usually older, so it will not construct a new map or new modification instantly. It will take time. Whenever they fetch or prefetch the data or upload it, then only road network gets modified. For one instance, I must say that in some things like Google might do much more frequently, but usually the case is like 1 month or something before they actually modify it. And yeah. So sixth, okay, we are just closing in. So sixth is shape detection, or shape or object detection for that matter. But object detection like cars are still very much a technical challenge to be done on the satellite images, unless you have very high resolution images, which on the range of 50 centimeter, 30 centimeter, but then you need much larger financial aspects to it, and also you need permissions from the government as well to use that level of resolution. But on the other hand, ships are larger than cars, so you can easily detect from wide variety of proprietary data as well. Especially on the 3 meters, you can do it. So, but some of the major challenges which you will face when actually training a model on ship detection would be, so you can see the orientation. Usually the bounding box that will detect the ship will be rectangular, as in the first case, horizontal object detection. But that is now how the ships are there. You can see now overlapping bounding boxes are there. So how do you fix it? Because when you train the model and you run it, you will get those bounding boxes, but you need a way to actually make it on the rotator object detection. Then only it makes sense. Otherwise, your ship detection, even though it is able to identify number of objects, it's not able to clearly identify where that is. And the reason why B part is necessary would be if you're tracking ships. Basically, if you're tracking routes for the ships, having a good bounding box around it, a clear, precise, is very much useful to trace the route where the ship is going. Okay, and why is it useful or something? Even for marine cases and defense cases, there is something called exclusive economic zones identified by the government, across the world. So this is where sometimes fishing is not allowed or fishing is allowed but not by different parties. So basically government is always monitoring these zones. And if someone, and these ships already have a radar or tracking devices called AIS, which transmits the data every few seconds or every few minutes, but you always have the option to disable it or even shut it down. Disable it, or sometimes it malfunctions. So the government wants to know whether someone has illegally approached your marine areas or someone is illegally doing illegal fishing. And in those related use cases, ship detection is very useful. You can take the images, you can see what is happening. So I'll just go to a very older example. Okay, this is one of the so you might have heard of Suez Canal obstruction. It was it led to quite a lot of losses, billion-dollar losses, and the reason was ship was stuck over there. And just a second, I think this animation is not it's playing to some extent, but okay. So if you see this, all these white dots which are there are actually ships, which it shows the traffic that was going across from there. Since it was not timely detected that the ship was stuck, so many of the ships that had already their route planned went to that area. And what happened was a cumulative jam, and also this entire thing they have to come back and go to another route. And that costed a lot of billion-dollar losses, majorly due to fuel and time. And if the ship detection can work pre-hand, these ship folks who are maneuvering the other ships can actually change the route in real time, or at least near real time, because this was stuck for I think more than a day, or I think 14 days or something. So it was stuck for a last time, but still the ship was going there. I think some animation more were there, but it's not working. It's fine. Okay, I'll just go to next slide. Wait. Okay, so the last use case is natural disaster detection. So in the earlier phase I mentioned about road network or road network detection, and the one use case that it also has on the disaster monitoring as well. And here it is tracking the building destroyed. So basically in case of disaster, what happens is there are a lot of buildings destroyed and a lot of claim. So basically buildings are destroyed. You have to send emergency services to that area. On the other hand, there are other aspects as well. All these financial companies who have given insurance to those buildings also need to determine what is the extent of damage that has been there, what was the previous, how did the building previously look like, and what is the damage extent right now. So in many of these scenarios, drones are being used, but if there is a large enough area, or if the destruction is very high where you even can't reach, drones might not work. So what you have to do is something like a building prediction model which detects building, and here it has detected how many buildings were there previously and then afterwards, and they use it to calculate disaster impact index, which determines how much has been affected, economic loss from the disaster. And these insurance companies then use this data to again go for the claim process and other stuff. Also, this is very crucial in terms of, if I must say, the road network. How can you use the road network in disaster monitoring? So if there is an earthquake or flood in some areas, obviously Google Map will not tell you that there is a flood or the routing will not work there. Google still has the old data. It will tell you, okay, you can go there. You go there and you will drown, basically. So there is a need of the R in case of emergency services to actually know where is the correct route or which route is actually available right now, because many of these routes would be destroyed, and now you have only limited number of routes to reach from point A to point B. And that information, as crucial as it could be, it can help in emergency services like ambulance and other stuff. And obviously if the damage is beyond where the roads are not there, you can always re-strategize to make use of just Air Force. So these are some of the real-time implications that can be done. And one more is fire detection. So fire detection is something that has been a menace since last 2-3 years, and there is always, even despite lots of technologies, fire is always detected almost like after much of it has been burnt, because there is no such so there are currently some folks have deployed IoT based services to determine when there is a fire in the forest or something. But in many cases the devices go off before even transmitting the data or some things like that. So in those scenarios, wildfire detection is still, even though it's a simple use case, but it's a kind of need of the R AI use case where using different bands, or in this case shortwave infrared bands, people are determining where the if there is a forest fire or not. But obviously then you have to determine in case of post fire or post disaster, you also have to determine how much burnt area was there to estimate the losses of the biomass or the forest area. So in this case, one of the models, it has predicted the mask, and it has done the prediction based on how much burnt area is there. So this is very crucial in terms of post disaster strategization and other stuff, where you can train a model and it can detect not just based on SWIR bands but also on other stuff, that okay, these are the burnt areas. Okay, so all the machine learning use cases. So I just covered the overall use cases, not going into the details of each of the technology or architectures or algorithms that can be deployed for each of the steps. But if you see, in most of the 7 use cases in general lie in these 7 ranges of AI use cases. These terms are technical, so yeah. Basically we have not covered data fusion and multispectral, but suppose automated feature extraction, ResNet. In the bracket I have mentioned what are the popular models, algorithm models that you can use to make implement that feature. So automated feature extraction is nothing but determining the correct features. So features is nothing but determining buildings, determining, so basically one type of some types of features you are trying to determine on a given image to classify them. So you have automated feature extraction, and ResNet and VGGNet are very good, have seen much more higher accuracy in terms of other models. Then data fusion and multispectral analysis. So data fusion technically means, so as I mentioned, there are different bands. Opticals are there, and there are multispectral, hyperspectral. But in case of many of these cases, you can combine these bands to actually make a new image altogether. So you can have an hyperspectral band which has a lot of bands, and you can combine some of these bands to make a new image altogether, which the camera or sensor did not support originally. And you can use these techniques to basically, suppose sentinel images are there, 10-meter resolution data to convert to another sensor's images. It's like converting, in simple terms, if I would say, you can convert iPhone phone capture to something like a Samsung phone captured image, or vice versa. But obviously it requires some of the image processing rules as well as the AI based rules to correctly determine the sensor configuration, and then you exactly simulate those sensor or transform the original image to the target destination images. Then there is semantic segmentation, which we use for land cover mapping. So UNet is very good on that purpose. And then temporal analysis and change detection is basically determining the change, such as urban in case of water bodies, if you're determining change in the water bodies or determining change in the buildings that are there, you can use RNN or LSTM. So these are very good models that are designated for this purpose itself. And then there is super resolution imaging, which is also called synthetic image generation. So as I mentioned, on the road network, we generated a synthetic, we exactly did not generate a synthetic image, but at least the colored part was a GAN based approach where you created a new image out of nowhere. But on the so that was one synthetic image. But on the super resolution part, what it means is you have a sensor which has a resolution of 10 meter, or basically it's not good, you can say. So basically I will down it to phones. So suppose you're converting 12 megapixel phone camera image to a 16 megapixel phone camera image. So basically you can upscale or downscale the image based on the different AI techniques. And how it does is, obviously this 10 meter data is looking at each pixel is 10 meter. Now suppose you tone it down to 5 meter, that means each pixel will now represent 5 meter. So the next pixel is actually empty right now. Since you have data only for one pixel, that is 10 meter, and I'm saying now how will it generate the remaining part? So it directly predicts based on the original image. So suppose you have a car, some part of the car is visible, and you're now zooming in and you wanted to make it high scale, so it should look a real crisp picture, but it doesn't have enough data to actually make a crisp picture, okay, because originally image did not capture that. But what it does is, based on the neighboring patterns that it learns, it will generate or predict it, the different parts. But obviously it has implications, like if you're generating the image itself, then what is the reality? So because if you're running the algorithm on top of something which actually predicts that there is something, but it is actually not there, it might not be actually there. So there are some ethical questions on super resolution, and whether the training on that part is, suppose you're training detecting fire or detecting buildings or stuff. So this, when you super resolve it, you're actually creating some information which was not present on the original data, and the way you did it was by predicting it. So you predicted something, and on top of that you're doing another prediction. So the authenticity of that prediction is now doubtful. So that is one of the downside, or maybe you can say questions of that. And then there is anomaly detection and quality control, which is related to any kind of anomalies, basically from the usual pattern. If you see something else altogether, you can all those use cases fall under this. And isolation forest or support vector machines are good algorithms that can. Isolation forest uses binary trees and other stuff to classify the outliers in one range, and then you can use those pixel values to determine something. And transfer learning for limited data environments. So transfer learning means basically you did not have enough data for a different use case. So basically, suppose you train a model to work on an urban landscape where there are a lot of buildings, mostly there are buildings and less trees, and you made the model such that it can detect urban changes, which are like buildings or roads and stuff. But then how can you make sure that it works on, and now you want to train a model which does the rural urban detection. So in rural areas you will have a lot more trees, the roads might not be concrete, so it will have different features from the urban areas. So there are two approaches: either you can start training from scratch those models, or you can transfer learning. Is basically in limited data is, now for rural landscape you don't have much data, but you already had so much data for the urban thing, and you trained a model for that. So now you will take some part of it and put it into the another model. So basically you're transferring, it's basically like a KT session but more advanced. So you're transferring the knowledge that you had from one place to another so that it's applicable for a different use case. So obviously it will have some downsides to it, but more or less it is good for the limited data environments. So I think many of the folks already know that there are tools like Google Earth Engine, which actually has a lot of data. You can directly run, this is JavaScript based code, and you can get all of the data free of, at least on the Google Earth you can get them free of cost, but if you're using their API you will have to pay. And then there is Sentinel Hub, which is like Sentinel is basically satellites from the European space agencies, and they have made their data free to use. So every 5 days it covers the entire globe, and every 5 days you can get a new image, and you can just play around the browser to see various different scripts that are already there, and you can also write your own custom script on top of it. On the below down you will have a custom script section where you can write different logic or algorithms yourself to play with the different bands that you have. Okay, so till now this was classic geospatial thing. I'll move to stuff that is a little bit more interesting. So As Aman mentioned, at SkyServe we are building edge computing platform. So we are basically building technologies that enables folks to run AI models directly on satellites. And I'm not just bluffing it, we have already proved it, and we have made it possible to run AI models on top of the satellites. And we already have 3 satellites currently in the orbit, 2 in the orbit, 1 in the coming future, that can task or process this stuff. But the question is, why do you want to process it on the satellites and not on the ground? So the traditional method is satellite takes the images, it captures the images, that images are being sent to their respective ground stations or their collaborative ground stations, and then they pre-process it to some extent, and then they sell those data, which are used by the geospatial analytics companies. I think folks agree, right? Yeah. So in most scenarios, this is the case. The problem with this is, even if you want to use some part of the image, you still have to purchase the entire image, because obviously satellite operators he captured an entire image of 200 square kilometer, and he will sell you that data because he is downloading the entire 200 square kilometer image, and he will charge you for that. On the other hand, if you have only use cases of like 40 square kilometer in that part, you're still paying for the rest remaining 160 square kilometer, which might not be useful for you. And similarly, in some use cases, there is, because of this entire supply chain which is very long in process, even though the satellite can get you a photo in 3 hours, but to actually get to your end, the geospatial end, it will take more than 3 hours. So suppose in your company you are right now and someone asks you, okay, we'll build this model, we need the data set. Satellite can give you in 3 hours, but you will not get the data set in 3 hours. You will get it most likely next day or maybe in 2 days, when that edge operator or satellite does its processing and sends it to you. In all these scenarios, you can see there is a time lag, or the latency issues are there, and also which also leads to a delay in the processing that you're doing. Okay, if you want to actively monitor a flood use case and or the earthquake use case, and today earthquake happened, ideally you should be able to get that image in next 2 hours, 3 hours, and do some processing on top of it and get the results directly. Then only it's useful. If you give them data after 1 week of processing, it's just like a report. Basically, it becomes a report of for the hindsight. So that is why we pursued edge computing. So we pursued in a way that you can do all this processing on top of the satellite itself. And what it also allows is it opens a plethora of options that are technically currently not possible. So something like, first is the cost reduction that can happen. So with the brains on the satellite itself, you can actually tell, okay, you need this area of interest, you need only 40 square kilometer. The operator, if they have captured an image, so capture it will do anyway, but the major cost is on the downlinking part, because that requires energy from the satellite, and also it is a long tedious process. It downloads at a relatively not very fast rate, but at a nominal rate. So satellite will charge you for that for the per GB cost or whatever that is. Obviously that pricing is not open, but usually that is one of the major factors they are charging for. So what if you can reduce the size there itself? What you can just get the 40 square kilometer image to you, and you can get charged for that. Obviously it will reduce the cost for you, it will reduce the cost for end user, and the entire pipeline also becomes much faster because the processing sum has happened there itself. And that is one of the implications, that it can make the applications cost efficient. And one of the cases, like even if the geospatial, if you see, AI has scaled tens or hundreds of folds in other realms, like chatbots, we have LLMs now, okay, and you have other stuff. But if you see in geospatial domain, we are stuck with these use cases and we are not able to come up with more use cases, or the general folks at least are not able to come up with any use case on their own. The reason is it is expensive. You and I as an individual can't purchase these images and, okay, we have a startup idea, I want to do it tomorrow. It's almost practically impossible. I'll just give one example. Bangalore area, 740 square kilometer, one of the proprietary data as openly available on the archive part is charged at around 2.25 square per kilometer. This is one of the company's actual data. So based on that, if you compute for the entire Bangalore image, that would cost you around, one image would cost you around 1,40,000 or something. okay, one Bangalore image. And if you are working on monitoring, suppose say you come up with a new idea, okay, that you will do from tomorrow onwards, you'll start your own startup and you want to do urban water body detection, that there are a lot of lake beds getting destroyed and real estates are building on top of it, or forests are getting destroyed. But 1 lakh for that you need continuous images. At least you can say you need images like 5 per month or something. So if you are actually, it costs around 1,40,000 for one. So that means for 10 images it will cost you around 15 lakhs per month. And for a normal folks or the organization, that is a lot of money to pay. And this is one of the reason I think that geospatial, even though AI has grown leaps and bounds on it, and if you see AI on geospatial domain research papers, you will see a lot of research papers, crazy research papers with crazy ideas. But on the ground, you can't implement it because the data itself is so costly that everything is just basically becomes a report or a research paper. But using edge computing, maybe it can solve a lot of problems on cost reduction, and that can help folks venture into this domain and actually build own applications. And even small enterprise or small group of folks can pitch in to make new innovative ideas that can transform this entire industry. So I'll just go briefly what we are doing at SkySurf. And so basically we have built 2 platforms. One is the ground station or the ground infrastructure, which is there called Surge, and one is called Storm, which is there on the satellites. So basically your models can come in. Your models can directly be put on this Surge platform, and that makes it space ready AI models. Why I'm saying space AI is because there's a lot of training and a lot of stuff that you're doing is on conventional machines, okay, which are different architecture than the devices being used on the satellite. So different architecture means different problems you have, and also different library versions, different environments. Obviously you as an individual can't possibly know all what are the devices being used on these satellites. Neither one can own and set up in their own house, okay. So we at SkySurf have built this platform wherein if you are interested, you submit a model. We have those devices in-house, and we have those devices. We can test and train on those data, and we can check whether this will work on that particular satellite or not. If it works, we actually deploy those models to the entire satellite constellations that we have, or the satellites. And whenever you want, you can do the tasking as usual. And suppose you want to detect some water bodies, or if some war is going on, you want to detect some areas, you just go through it there, you task it, okay, I want an image, I want to classify water body, and I want to detect buildings. And what you can do is you can just get that segment output, or the JSON based output, or the segmentation binary outputs on top of it. So that reduces the size a lot, because what we have seen almost like 5x reduction. If your original image was suppose say 5 MB, 50 MB, you can get the entire insight out of it in just 5 MB. And that is a massive reduction in size, like from 50 MB to 5 MB, you're getting the entire stuff. So this is what we're doing. And yeah, this is just one. What happens, like if someone submits the model and you can put a lot of details in the platform and directly go to that. And what I was saying on the segmentation part is the AI model can be done on top, and you can get the water body, town, building, vegetation, road, railway line, and all those stuff which are usually do on the ground can be done on the edge, and you directly get that insight. Now you as an individual can sell these insights to someone else, or you can directly use it, but the resultant cost would be less, or the latency would be very low, because now you've removed the pipeline, or at least to some extent you have reduced that pipeline timeline. So yeah, so that is what we do in SkySurf. So alright, so that is the conclusion. Okay, sorry, some of the things I'm missing here. Okay, so that is the conclusion. What I would suggest is, many of might already know, these are the 2 links over there. I can ping you in WhatsApp or the separately as well. Satellite image deep learning. You can follow this GitHub repository. It is very good. It has almost close to more than 100 techniques and data sets for different AI use cases in geospatial domain. It has links to the research papers, link to the code, and also you can basically clone it in your repository, clone the into your computer, run it, try to modify it. So it is a very that Git satellite image deep learning. It's a very good repository to watch out for, and it usually gets updated time to time. All right. Thank you.
So if there are any questions to Rupesh, please feel free to ask him now. Anything about yeah, please.
You had an image few slides before where there are few marks over it and roads where dark purple and vegetables to be yellow color. That image, did you use different thresholding levels based on frequency?
Yes, but it was mostly on the AI. It was based on the algorithm. So basically, yeah, but it was trained separately for each classes first, then combined and then retrained again, and then finally did some other modification for the thresholding for different stuff.
So this different vegetables.
Okay, for the vegetable part you're saying, for the agriculture or for the image segmentation, which has.
Image segmentation.
Okay.
You said that roads would absorb different frequencies. Absorb different frequencies, right? So that using that different frequency, you did thresholding, right?
So there are two methods in it. If you have enough data for the frequency, so basically frequency methods are only majorly possible on hyperspectral stuff, because then you have lots of bands to play with. So basically you have different frequency for each, and you can play with different bands and how it reacts with each of the stuff like road and stuff. But in scenarios like if you have RGB image, you don't have that liberty. Now that all those, you only have 3 bands now, red, green, blue, and now you have to play around these only. So the other better method would be train the model such a way that it is you put all the road stuff, okay, put all the images stuff, vegetation and other stuff. So the RGB configuration or the pixel, as I said, all these are matrices, right? At the end of the day, it's matrices, 2D matrices with values. So you train them accordingly, because the band wala value to you don't even have right now on the RGB case. But obviously if you have hyperspectral data or you have so many number of different bands, you do it based on thresholding. It's I would say easier, but it's a more solid approach and more deterministic approach. But if you don't have that data, then train out on RGB with different matrices values that you have.
So you were saying we have to use different for detecting road. We can use road masks, right? Building masks.
Yeah. But how you will get the mask is the question. Normally you won't get the mask. So basically you only have RGB image, right? So RGB image में सब वैसे दिख रहा है. Only difference is the color pixel values of RGB that changes how it looks like. And if you look at each individual pixel, at the end of the day, it's just RGB values. So even though visually you can identify it as a road for this, but for computer it is best that you parse it as a 2D matrix, put it in a neural network instead of the thresholding method, and then it will do its job much better than this.
I have one more question. You said that where would I get the mask, right? So I'm working on a project to detect tumors on a lung CT scan. So that I already have a mask for the tumors. So I have our unit model is unit model. So my question is that to detect multiple tumors अगर मुझे एक ही CT scan में detect करना है, तो should I use multiple masks for all the tumors in the same city या फिर एक city में normally एक ही mask use करना है?
You put everything in one only. That is the. But is the tumors different? So then you can do is on the segmentation part. What you do is you assign labels to each one of them. Suppose a tumor X है, तो उसको value like you put it as 1. No tumor 0. This tumor you detect like X is 1. Tumor Y is 2. And what you do is when you parse it, right? So in the image, so you're writing a mask right now, right? You're writing a mask and उसमें that tumor has a value in it. Okay. So now assign different values to each of the based on what you detected. So either one step is you put several different masks for each अलग-अलग type का tumor. For different tumors you produce several different masks. So okay, tumor X, this mask is there. So 0 means no tumor, and wherever that white dots are there, you can say that there is this tumor. Then there will be a second mask which will correspond to different tumor, or combine everything into one. But for each different tumors, you assign different pixel values when you are writing on the using image algorithms.
और अगर मुझे अगर generalized detection करना है, तो then I will have to put all the masks in the same city, right?
If you want to if you're also using this as a training or something, if I must say, then if you actually combine it and then do training, because what will happen is if you do training separately, I'm supposing you have a mask for each separate also, right? But train everything into one model, because what will happen is otherwise it will overfit into one of the tumors, and it might so happen that it is not able to classify it when you're able to see different tumors effect. अगर एक साथ सारे मिल रहा होगा तो it might misclassify it. So because your model does not have that much data points to actually correlate between different types of tumors. So you in the training set itself you have different types of tumor mask combine into one, then train on top of it, and then test and validate. Okay.
I just have a follow-up question. The RAM monitoring image segmentation, was that work done by you or cited from somewhere else?
It was cited from somewhere else, but I have not mentioned the proprietary models that we have developed in-house. So we also test somewhere, but I can share the link of it. So it is the mentioned where the GitHub link I mentioned, it is there in that one.
I just wanted to ask how large was the training data set?
It is, I need to check, but it's a big data set. I think 8 or 10 GBs around.
It might have involved the mask file or labeled data as well, right?
Yes, it has it. So it was I think part of one of the challenges which was there in Kaggle, and from there I read an article and then it was sourced from there. So he made a model on top of it, and he used one of the research papers also, and he implemented that research paper with that data set which was present on the Kaggle.
Can you recall how was the annotation done, the labeling?
So it was mostly on the segmentation part. It was just like that, segmentation mask kind of stuff with 0, 1, 2, 3 and all those values you put.
Was it done manually?
For initial the Kaggle data set, I'm not sure how they created it, but I think someone has done it manually for the first time.
And for training the data, whatever she has told, okay, how large, what is the kind of hardware did you train the model on? Like, was it like an NVIDIA GPU processor with how many cores, and for how long did it run, and what was the total expenses?
For this model or for the edge processing models that I was talking about? For
whatever you explained in this, right? Whatever your model is, like whatever you are trying to do.
Yeah.
Agricultural thing, right? Okay, so what was the hardware used in this?
Hardware.
Like CPU or some kind of a GPU?
CPU.
If you go on Colab, you can instantiate different kinds
Yes.
of hardware, right?
Yeah.
So which specific hardware did you use for this?
For the stuff that we do at SkyServe, or basically on the edge processing, edge processing stuff, we are not using any of these core the Colab instance or anything, because these are anyway very large instances. This cannot run on the satellite. I would just say it's basically ARM based. Cannot directly name the exact device that we are using, but it is NVIDIA or AMD devices, basically NVIDIA devices, and which are much more in a smaller size, like this much. So it has, I can tell the configuration though it's open. Just a second.
No, because you said that there is one data set company in Bangalore which charges like 5 lakhs, whatever you.
That data set was from Planet Labs. That pricing. Yeah.
Right. So if you calculate the 15 lakhs, and then now you come to the hardware, right? If you are doing something enormous like this for a Bangalore area size 750 square kilometers, if you calculate that 15 lakhs for 5 images, and then you keep this hardware, you calculate the sum total, it shoots up, right? Shoots up. The cost, that is the amount that you are spending for such minuscule of imagery data, shoots up. Right? So which hardware is, because on Azure, if you go on Azure, go on AWS, GCP, they have several different instances of hardware. They say that we pre-package this hardware, you have PyTorch, you have everything, and rental it will come to this much. Like that they keep.
Yeah.
And it is confusing to a normal user.
Yes.
No, it is very confusing. And I have also seen people on Twitter saying that if you go to AWS, your entire dollars will go away. You have to spend it all.
Yeah. So basically, actually, AWS has a service which provides this edge model, edge hardware, I would say. So there is a service called SageMaker. So it has list of, if you go there, select any model. So what they claim is basically if you put any model, it will optimize it for that hardware. And this but that SageMaker is there. But again, that hardware devices would be a family of any NVIDIA devices, which are like similar to Arduino based, but more complex, which has GPU cores also. And this. So in terms of processing power, obviously these are less than what directly Colab instances or Azure directly provides.
So in your company, how much were you spending for doing these things? Like,
I would say it's pretty low. I mean, I would say it's not even.
maybe around 10 lakhs a month, like, or
No. It's the device. Yeah. Yeah, I can talk to you personally. I will talk to you, but it's very.
No, I was talking about the hardware, because on the hardware we can.
No. If your question was the hardware cost plus image cost that you're saving is equal to the image cost itself, no, it's not. It's still less, because hardware is. But the hardware is very cheap. If I would say hardware is under 1 lakh rupees, under 1 lakh, 2 lakh, then, and it's a one-time investment or something like that. So you can go ahead that one.
Okay, thanks.
All right. Yes.
I think we can take questions.
I will answer personally. Yeah,
No,
I think.
because we are running out of time and we have 2 more speakers. So thank you, Rupesh.
Okay.
But we
I'll
actually
answer
started late, and then sorry guys, but you can ask questions later on. We have a networking session after this. You can ask questions there. Now before we move on to the next presentation, I just want a quick introduction of everyone. So might as well start from here. So I'll start first, and then you guys can carry on. Just a small introduction of what you do, where you're from. So my name is Aman. I work at Galaxy Space, and I'm one of the organizers of Let's Talk Spatial. So yeah, please.
Hi everyone, I'm Sumesh and I work at Galaxy Space with Aman, and I'm one of the speakers here, so I introduce Mr. there. So, thanks.
Hi everyone, this is Bhumika. I also work at Reactor Space and I'm head of AI and web division there. So I work on image processing and AI.
I'm working as a geospatial analytics, and I'm
Yes, a little louder, everyone.
Hi everyone, I am Aman. I am working on US analyst in Geospatial.
I myself, Devansh, I am working in Discover Dollar as a data scientist, and basically I am from Uttar Pradesh. Thank you.
Hi everyone, this is Sumesh. So I'm working as a geospatial data scientist at Paraha Climate AG. So there we are working on regenerative agriculture practice monitoring using resources.
Hello everyone, I am Rajni. I am also working at Paraha as a geospatial data.
Hello everyone, I am Rohit Rajan. I am working in IIHS Bangalore.
Hello everyone, my name is Deva. I also work as a geospatialist for that IIHS.
Oh, so now me? Yeah. Hi everyone, I'm Srinivas and I'm collaborating with my colleagues who are in the process of starting their own venture into mobile space, generative AI, everything. Not this domain, not related to geospatial. But this domain interested me a lot, so that's why I came to attend this event to see what we can do or what kind of apps we can develop into this space.
Thanks for coming.
Hi everyone, I'm Lavelle. I work at Galaxy Space as geospatial analyst.
Hello, my name is Koushik. I work in Galaxy as a business development manager.
Hello everyone, myself Gabu. I work at Satya Companies, and I also one of the organizer of this event.
Hi everyone, I am working in DS management in geospatial. Hi everyone, I am Rupesh. I am working in
everyone. I'm a freelance machine learning engineer. I'm currently working on a long-term segregation model. And I'm also working on an idea related to blockchain. So, because I like AI, so that's why I say it.
Hello everyone. Myself, Lavelle. I work as an analytics analyst at user labs. Mostly I work on data preparation and activities.
Hi everyone, I am Reactor. I work as data analyst for Union. Basically, we analyze government data.
Hi everyone. I'm Rohit. I'm working as a geospatial analyst at Bangalore.
Hi everyone, I am Kumar. I am working as software engineer at Reactor.
Hey guys, I'm Kalash Mandale. I'm working at Reactor as product manager.
Hi everyone, this is Ayush Agrawal and I'm a student pursuing data science from IT Madras.
Hello everyone, I'm Nasari at Meetup.net. Slightly different area I know, but we provide services for within our company to data scientists. So I basically wanted to look at what workers you guys are using, what essentially is happening in this space. That's what I'm doing.
Hi everyone, I'm Reactor, working as a GIS analyst at AU.
Hi, I'm Mitali. I'm working as a mid-central scientist with this team at Bangalore. Hi everyone, I'm Diona. I work as a geospatial data scientist at Bangalore. Hi, I'm Helen. I'm a freelancer geospatial data scientist.
Hi everyone, I'm Gaurav. So I'm a software engineer.
Hi everyone, I am Khaled. I work at Spatial as a systems engineer.
Hi everyone, myself Rupesh. I work as a lead software engineer at Spatial.
Hello everyone, I am a senior data scientist at the London Stock Exchange today. So this is totally alien to me.
Hi everyone, I'm Ramya. I lead product development at a non-profit which is focused on humanitarian data.
Alright, thank you everyone for your introduction. Our speaker has just gone to washroom, so meanwhile, why is okay? So we'll start in just a bit, but the washroom is here. You can take 5-minute break and we can start again. Snacks and tea will be after third session as well. So meanwhile, if you want to just have a break for 5 minutes, then we'll start with the next presentation. Cool. So we'll have our second speaker, Koushik Kumar. I'll just introduce him and then we can get going with the second presentation. So Koushik is working as a GIS analyst GIS engineer at Spatial. He has over 1 year of experience, and so I'll just tell you how we contacted Koushik. We organized a hackathon along with SkyServe last month, and that hackathon was based on edge computing. So you have to deploy your models on edge on Spatial's platform, SkyServe's platform, and then so Koushik and his team actually won the first prize in that. So he had the lightest model for farm detection, and also were able to deploy on edge successfully. So that is why I wanted him to present how he made the model lightweight, and also how he detected the farm boundaries. So presenting Koushik to you, he works extensively on PostGIS and Postgres, and also on JavaScript functionality. His accomplishments include geocoding and reverse geocoding, and also PyQt project for car number plate detection. He has completed multiple projects, Python projects, and has over 90% client satisfaction by reducing manual labor. So please welcome Koushik onto the stage. Fine, no?
Hi all, good morning. Today I am presenting the deep learning based approach for farm boundary detection. This is basically a CNN based model. I will basically talking about the quantization and how to make a model edge fit. So let's start with the model. Okay, here I have the topics. First I will start with the unit architecture, then I will make a comparison with the VGG and ResNet block architecture, and then I have some Python implementation of those VGG and ResNet block. Then I will go for the model quantization part. First we will know about what is quantization and how the quantization happen in mathematics and dequantization also. Then we will see the types of quantization. Then the 8-bit quantization using PyTorch, the Python implementation we will see. This you can see the okay. Here you can see this is a unit model. This is a very popular model to basically semantic segmentation and also binary classification tasks. Here we have configured the model to basically take input of 3 channel input at height to with this 256 and 256, and it will make the output as a 4 channel output. Like first channel is the mask, and the second channel is in the output channel, the second channel is the farm, and the third channel is the not farm, and the fourth channel is the farm boundaries. Here you can see the model is split into 3 parts: the encoder part, decoder part, and bottleneck part. The bottleneck part is basically the junction of encoder and decoder part. Okay, there are some skip connections that is from encoder to decoder to basically transfer the gradients while updating the weights. It's basically for to accomplish the actually balancing gradient problem. Okay, here the actual model having taking the input as 3 channel input and taking the output as 64 channel and in the first VGG block. Then we are applying the max pool. Then the second convolution block, it's taking 64 as input channel and 120 as output channel, and it's going on up to the bottleneck. And the bottleneck part, it's taking the 512 input channels and 1024 output channels. Then we are doing the upsampling and concatenating the encoder output channels to the upcount block, and then we are using the VGG block to basically convert those features and upsample those features. And here the output is basically 128, 664. Then we are using a softmax classification technique, softmax layer, to basically classify the probabilities. The next, this is basically VGG and ResNet block. First is the VGG block. It has conv layer, then ReLU activation function, and then conv and ReLU. Then we are applying the max pooling operation. This is very uniform model and it's easy to understand. It is firstly very fast, and it has some problem with vanishing gradient problem. So actually, when there is a relation when the model depth increases, the accuracy increases. But in VGGNet, the researchers found the problem that the model depth is increasing, but accuracy is still going down. So that the problem is the vanishing gradient problem. So they come up with a solution that is basically residual connection. You can see the ResNet block here. First there is a conv, second is a conv, everything is same, but from the first channel there is a shortcut connection, and after then we are adding that. Okay, so basically that is for the gradient flow. Okay, and it will remove the vanishing gradient problem. Okay, here is a PyTorch implementation. First the VGG block, I have created a class, then some convolution block and along with ReLU, and the forward method. Here it is taking the input as x, then it is passing through the convolution, then ReLU, then convolution 2, then ReLU, then the max pooling, and we are getting the output. And here is the ResNet block. It's a little bit complicated. Like we are started with some convolution of a convolution block, then we have started the batch normalization, then we are doing the ReLU activation, then we have applied that convolution to then batch normalization, as then identity mapping. That is basically the skip connection, the shortcut connection to flow the gradient over the network. Okay, now the model quantization. The model quantization technique is basically to convert a floating point model or floating 32-bit model to a int 8-bit model, to basically faster computation and inferencing. When the model works on like integer based integer 8, it's basically inference fast. So the primary goal of quantization is to reduce the precision of the model weights and activations from floating point, typically 32-bit, to lower bit. Basically we do the 8-bit quantization. Actually the quantization is basically to make the model edge deployable. And here is the quantization formula. There is a two quantization parameters like scale and 0 point. We use to quantize quantize and dequantize the weights and activation values. Okay, to get the scale, we may know that minimum min-max scalar. There is a min-max scalar function. So the scale is basically that formula. It's taking the maximum float from the weight and the minimum float from the weight, and for the unsigned integer, it's the value range is 0 to 255, and for simple integer, it's the value range minus 128 to 127. Now if we input as minimum maximum float is 1.0 and the minimum float is minus 1, then we are getting the scale value is 0.00784. This is one quantization parameter, and this is the another is the additive parameter. One is that is 0 point. Basically, it's take the minimum int that we are want to quantize floating point to integer. That is the minimum int. It may basically 0 or it might be also minus 127. And this is the formula to get the 0 point. This is basically like bias in our linear regression formula. Here is the formula applied. This is the quantized value. Here we are applying the input as like 0.5, the floating point value, and we are adding the scale, that is 0.00784. We are adding the bias, that is the 0 point, and we are getting the quantized value as 192. Then we can do the dequantize also. Like we can take as input 192, and we can give we can apply the formula. Then we are getting the dequantized value. Now you can see that 0.5 is the input, and after quantizing and quantizing to integer space, and from integer to floating point, we are getting the value, but there is some error. That is called quantization error. The quantization error for that this case is 0.00175. Okay, there are two types of basic quantization technique. That is post-training quantization. That happen basically where we have a model. We have a floating point model. When we create a model, we basically have a floating point model, float 32-bit model. After training, we can do the quantization. That is post-training quantization, but there are some cons. That is, it may lead some accuracy, a significant accuracy drop, and this is not good actually. This and there are also a quantization technique. There is quantization award training. It's basically do the quantization and dequantization while training. So the loss function and optimizer will go the right direction and create the gradients. That's way, and it has better accuracy compared to that PTQ or post-training quantization. Okay, this is the diagram of the PTQ. First we have a pretend model, then we have attached observers. Observers are like for daily min max temperature, we have some like thermometers. These are like observers. That give some minimum and maximum temperature for a day. This is also like same observer. There are some different type of observers, like histogram observers, min max observers. It basically calculate the min max observer basically calculate the global mean and max weights. Here the max float, min float. Basically the observer will create those min and max float, calculate basically. After the pretend model, then it is attached some observers. Then we should have some calibrate data set, and we have to set the model as evaluation mode. Then we can do the calibration, and after that we will get the quantization model. In the calibration data set, the model the observers will calculate the floating mean and max for the whole calibration. In the whole calibration, and it will find the best minimum and maximum value for quantize the model, and it will calculate the scale and 0 point according to that and quantize the model. The next part is the QAT. Here you can see after the input the weights are coming, and it's doing some quantization, and it's representing the value as integer space value, and then it's doing the dequantization, and then we are having some different blocks in different weights, and this is the output, and it will calculate the loss based on the loss function, and the gradient descent or any optimizer will optimize the weight or optimize the weights. And this is the theoretical explanation. The code explanation is starting from here. So these are the necessary imports, and I have inserted a class that is residual block. I have already explained, and this is the encoder part. That is basically taking the residual block and max pool, and it's creating the encoder, and this is the decoder block. And finally, we are using the ResivNet. Okay, when the fuse of the modules, why it's needed actually? When we are doing the convolution operations, there are some we use convolution first, then batch normalization, then ReLU. We can do all the processing in as a one module. So if we not do that, when we do quantization, it will quantize all of the weights for all of the layers quantize all of the modules separately. So the quantization error will be much higher. So we should first fuse those layers, that computations will happen together, and then we should apply the quantization technique. We are applying this is some helper function I have used here. Then this is the data loader part that load the data. And we have annotated some images with some images, and these are the levels. The 0 value is the background value. Here is the color is blue, and the green is the field, and the yellow is the field boundaries. Here the blue is the non-field areas. We have annotated those. And we have also made a custom loss functions to basically actually for semantic segmentation, the focal loss, if our data is imbalanced, basically to say all the pixels are not falling exactly in right proportion. There are some proportion mismatches, like it is like falling 20%, it's falling the field class falling like 50%, the other class falling like 70%. So we should have some kind of loss function that can handle this type of inconsistency in the data set. So this is the focal loss we have used with gamma 2. This is the final training loop. The training was done in GPU based system, so that we have inserted the device, then we are sending the model to the device, then we are setting the model to evaluation mode, then we are applying the fusion of the modules or layers, then we are taking the configuration from the x86 architecture, and then we are preparing the model to quantization in training mode, and we have set the optimizer as Adam with landing rate 0.0008. The criterion is the loss function. There are some weights, those are like 0.2 based on the classification hardness. The gamma is 2 here, and the reduction is mean, and we have taken 10 epochs just for testing, and this is the validation result you can see here. And after that, the process was done, is the quantization our training. After the model training, you have to set the model in evaluation mode, and then you can you can convert the model into 8-bit. Yeah, thank you.
Any questions for him on what his model was doing? Please feel to ask. Yeah.
So you trained the model, and then, as Aman mentioned, you made the smallest quantized model. Yes. Did you see any significant change in accuracy of the previous model and quantized model?
Yeah, not significant change, because this is quantized our training. So the significant, there is a drop of like 0.5 in accuracy, we have used the IOU method to validate the result. There is no significant drop, I can say.
Is it because you use the fuse models or?
Yeah, the fuse model, actually the error accumulation will be less, because if we not fuse that model, the quantization and dequantization will be applied for all the layers. Okay, so if you fuse the models, then all the means calculations will be in one module, like a one module. If you fuse this model, so the quantization will be before that, after that. Quantization and dequantization will be before that, after that. So the error will be less.
Rupesh, your question.
May I know which data set we used to train this and what was the spatial resolution of the data set?
That your team has shared that data, that planet 4.7 meter resolution data, I think.
So this is trained on 4.75.
Yes.
And also, how did you post process it? So I see a lot of gaps in between.
Yeah.
So did you do any post processing?
Actually, the post processing pipelines was there, but it is not included here. There are some dilation process first with 3x3 or 5x5 kernel. That is basically hyperparameter one. Then we have used the connected component analysis to connect all of the like pixels. Then we have applied that featureization.
Got it.
Yeah.
You said that you use focal loss curve to data set of imbalance, right? So can you explain more on that? आप किस parameters में आपने decide किया? In which conditions that you use?
Okay. The parameter values, right? We have done the retune hyperparameter tuning. Okay, you may know the retune. Okay, we have taken all of this, like 1 minute. These are all the hyperparameters, right? Like 0.20, 0.6, 0.88. Okay, these are all optimized weights. We have did the hyperparameter tuning for those numbers.
My direct question would be, why did you use focal loss?
Because the cross entropy loss using the validation accuracy was not really satisfied, so that the focal loss was better for that conversion. Actually the data set is imbalanced totally. Okay, and the proportion of the all the classes are different. So focal loss have a gamma value that is basically the loss function. Basically, if we give the gamma value with 2 or 5, like I can because I forgot there's how you can balance that data set, because all the proportion of the pixels in one data set.
There are more pixels and there are more.
Yeah.
So focal loss would help put more attention on things.
Yes.
Less attention on the layer.
Yes.
Yeah.
What is the minimum system requirement for running this model? How much time?
Minimum system. We have tried with the Kaggle GPU P100 GPU, but after quantization, I think 8-bit, whatever the system, 8-bit computable, it can work, and the model size also like 10 MB or kind of. Before quantization, the float 32 model was like 36 MB. After quantization to INT8, it's about 10 MB or kind of.
And what is the overall accuracy you got across all classes?
Actually, we can say the accuracy because our validation data was not properly annotated. There was a lot of error in the annotation. So the accuracy maybe more than like 60% in IOU. The MIOU I'm taking. Yeah.
How would the model quantization would impact dice code?
Dice code. This is actually a validation matrix you are telling about, right? This is a validation matrix.
Yeah, he's telling it is a validation metric, right?
Validation metric, yes.
Okay, I not aware.
You said that for IIM you had 60% accuracy, right? If you haven't used model quantitation, about accuracy in answer, and if you didn't use model quantitation, how much performance can calculate would it improve your IU or
no, it will not improve. Basically, it will improve the memory consumption and the fast inference. It will always impact on the accuracy. Okay.
For DSC, you didn't try DSC?
No.
Any more questions? All right. Yeah. Thank you so much, Koushik. All right. So now we'll move on to the last presentation for today, which is on. Let me bring the slides. Multimodal vector search for geospatial intelligence. So I'll introduce the speaker, who is Sumesh. So Sumesh is working at Galaxy Space, has been involved in product development and research in deep learning and geospatial analytics for sustainable development. Before joining Galaxy, he was a research engineer to build the world's first diagonally auto-scalable cloud for DL applications. He is actively involved in FOSS community and also FOSS Asia, Hugging Face, NVIDIA Jetson ecosystem. He has been recognized as to be the top 25% innovators in Intel Software Innovator Program. So please a round of applause to welcome Sumesh.
Good afternoon, everyone, and thanks for being here. Thanks, Aman, and Let's Talk Spatial for inviting me. So, my topic for today is multimodal vector search for geospatial intelligence. Right. Before we even understand what this topic is about, I would walk you through a basic idea of why this technology is needed. What is the problem that we are trying to solve? And why exactly geospatial community needs this kind of a technology right now. Right. So I'm from Galaxy Space, so I'll talk a bit about what we're doing at Galaxy Space. We're building the world's first hybrid sensor satellites. By hybrid, I mean, like our fellow speaker Rupesh said, there are active and passive satellites which are built in the world right now and being deployed even. But we are going to build active and passive satellites both into one payload and deploy it on orbit. So what is the use of it? You will get a different type of data set, a fully novel data set, which will, maybe give you advantages of both the data sets with a single processing pipeline, or even other unknown, accuracy results or better analytics for certain cases. So there is a lot of exciting things going on at Galaxy right now, and you can follow us on LinkedIn or even visit our website for the updates. I'll describe the outline of the presentation just to understand what we're going to get through. We'll define the problem, we'll understand what is the problem in GIS context, we'll understand with the help of a good analogy that all of us can relate to. We'll understand what is the solution, what is the nature of the solution, how does the solution work in terms of how humans learn, what is the steps to go about thinking in this process, and understand how the deployment or the technical aspect of it is. Right. The problem. So, according to the International Data Corporation in the world today, the time spent on searching for an employee or an average analyst in the world is around 30% of his workday, right? That's around 2.5 hours of searching that a person does for the information that is relevant or needed for that person. And because this time is required for searching, getting the information, getting access to such information, there is estimated loss of 2.5 to 3.5 million on an average every year for all the enterprise customers, all the enterprise clients out there. This statistics was around 2022, in the year 2022. I could not get a updated one, but after that, due to the advent of new AI-based search techniques, or basically a search engine, that is Google, employing AI-based techniques to make search accessible, make information more accessible to people faster, this might be reduced. But what we are not seeing is this improvement has been happening in all verticals, let's say in software, in operations, e-commerce, or whatever verticals you take, but we couldn't see it in GIS. I don't know the exact reason. Maybe this space has been just come out in a few years back. Because earlier it was only consolidated to government activities, but now private players or startups are coming into this space, right? Even to mention the advances that has been happening there, we have InSpace, that's a government body initiative by ISRO to facilitate the startups coming in the space tech sector. And they, in their national policy for space tech ecosystem, have mentioned that data dissemination and access to data, democratizing this data to the people, to common people who don't even understand what GIS is the need of the hour. And that is exactly what we are going to talk today. So in the GIS context, the problems that we see for analytics or people who are involved, especially in GIS softwares, is heterogeneous data sources, meaning we don't really understand where the data is coming from. It's very ambiguous. Unorganized data repositories, which is you have multiple sources, all in cloud maybe, or maybe you have it in physical drives or NATs or whatever you call it. Ineffective data categorization means you don't really understand how the data is categorized. You have to browse through every one of these data sets and try and understand what is the metadata about. So typically if you go to any other data dissemination platform like Up42 or S3 or such platforms, you'll always see that the GIS data, the image that you do the analytics on, is totally different from the metadata. So how do you go about it? You go search in the metadata, find out the information about the image, and then download it. Right? That's a very, very crude way of doing it. Now imagine you accessing some information about other image verticals. Let's say if you want to access your photo, you wouldn't want the photo to be a different data, and the metadata of the photo, like the dimensions or the specifics of the photo, the width, height, to be a different data. You have to have that flexibility in which you can access this data using a single service or maybe some mechanism. That's what poor metadata to image mapping is. Inefficient ARD qualification, which means ARD is basically analysis ready data, and when you want to do analysis, you want to make sure that the data you're using is very apt to the use case that you're solving. So when you say that you want to make an analysis use case, you basically want to have a certain kind of aspect of quality designated with the data set. So let's say if Sentinel-1 or Sentinel-2, which are ESA satellites out there, they are providing that kind of quality, you would prefer those satellites for your analytics, right? And lack of contextual search. So these are the problems that we identified, for the developers or the analysts in the GIS community, and that is why that is what we are trying to tackle. Before we look into the further details, what I'll show is something that you can relate to. Right? I guess people here have already used Amazon, Flipkart, all of those platforms for online shopping or something like that, right? So this is just a mock-up of that, and what I would, what would you guys like to search? Is it something for gifting, or does anybody have a thing to search? Nothing? Maybe we would need coffee for that. Okay, let's see coffee. Right. So if you can see, this is text to text search, which is basically a search for some input text that I put here, and you would see that what are the Stack Overflow scripts for coffee. Now you wouldn't definitely find coffee in Stack Overflow. What I'll do is I'll just take this text, go to text to image, and then search for coffee again. So what do you get? A lot of products which are related to coffee. Now, have you ever wondered that if you put a simple word like coffee, or let's say tea, I'll change it to tea as, let's see what comes up. Right. Right. Can you see the kind of products that you're visualizing? You know, the sheer mechanism of identifying what the user wants from keywords, translating that into an image or the kind of image that are related to it, will give you an idea that how advanced the search technologies that these companies like Amazon or Flipkart use. Right? It's not just keyword matching. It's not simply getting this and storing this in categorization. It's all, you know, understanding the nuances of what you want to try and how do you want to visualize your search. So you might also see recommendations that comes in these kind of platforms, right? When you search about something, you get recommendations that is related to or remotely related to your search. So what we intend to do here is develop a similar platform for GIS. You know, try and understand how can we access this data without having a lead time. So we conducted a survey last year, and we found out that an average GIS analyst would require almost 8 to 10 minutes in the most advanced platforms available there to download data and try and find out if it is apt for the use case that you are solving. Right? So what did we see here? We saw that any e-commerce website will give me personalized experience, intuitive product discovery, contextual recommendation, real-time interaction, and visual search. Right? Okay, we didn't cover visual search, so I'll go back and show you. So let's say if you want to have a dress, a jeans like this, a similar jeans like this, your friend wore a jeans one day, and you are thinking that I also find a jeans that is in similar nature. So just select this image and you'll find a catalog of all the products that are similar to this one. Right? Now imagine the possibility that if I have a machine learning model to train and I want to have lakes or rivers or all of these water bodies based data set. So instead of going and curating this data set myself, I can simply go to this platform, put a sample of this image myself and access to this data. Right? So as of now, whatever e-commerce and GIS platforms have, why did I take these two? Because fundamentally, if you will see, both of these deal with data. E-commerce platform have product data. They have a database of all the products that you want to access. GIS is also a data set. The only difference is e-commerce products are tangible and GIS products are intangible, right? So this is the problem that we saw. You know, not able to access the data, not able to get into the understanding of which data set is suitable for what use case. What is the solution? Intelligent search. We just try and understand how these e-commerce platforms work, use that technology, and employ it for the betterment of GIS community, right? So to give you an idea of how this technology has evolved over years, intelligent search, it started with keywords-based search, then it got to cognitive search, then to language-based search, and now it's something called neural search. Keyword search was basic semantic mapping of what are the similar synonyms or related words, so you could just understand the embeddings, basically the distance between similar words. You would use those concepts like cause and similarity to get the most related terms. Cognitive was much more advanced, and similarly language-based was much more advanced. So in cognitive and language-based, it was most generic, so you wouldn't be restricted to a certain language or a certain domain. You could basically get the data and search it across different domains. Neural search particularly is something that we are going to look in this session, which is more focused towards multimodal neural search. What is multimodal and what is the technology there is something that we are going to discuss. Right? So if you look at neural search, you'll find that it is also called as vector search or hybrid search. Right? What is it exactly? You have a corpus of data that with you. It may be audio, it may be textual, visual, or any kind of data. Now, what if I create a latent space, or let's say a very niche dimension in which I can visualize all of this data in a single graph, right? What if I can connect them together and try to identify that if a textual information or a corpus is there with me, let's take the metadata of a satellite. When you download any data in GIS, you get the TIFF image, you get the metadata. Now, what if I can associate the metadata with the TIFF, or even other data like, let's say, video? Maybe in future we will have a real-time visualization of a video-based stream of satellite data. What if I can create an embedding or a network between these and then facilitate search which would encompass all of these together, right? So, how did neural search come into picture, or why exactly we are thinking about this technology is, it's the basic nature of human, right? When you associate any activity, any stuff that we want to do, you would not really employ only one of your senses, right? What you try to do is you look at something, you listen the voice, or you try to talk about it, and that's when you get the complete picture of everything, right? So our world models, the way we understand models is through multisensory input that comes naturally to us. We have 6 sensory inputs like taste, touch, hearing, vision, all of those, right? Then we combine and interpret them to get a coherent understanding of the world. And since this is a fusion basically of the sensory information that we gather, it makes us a very good few shot learners, right? You might have heard about one shot learners or multiple shot learners. What is that? In a single pass, if we can make a prediction out of a model, it's called a single pass or a one shot learner, right? We are inbuilt one shot learners. We can understand and take the information in single go and then process it. So what you're trying to do is getting the same intuition of human learning for neural search, right? So just for an example, an apple can be an apple that you eat, or the apple that has a device, basically MacBook. So first of all, I would like to explain what is modality. Modality is nothing but a different type of data. So when I say multimodal, it means I'm dealing with more than one type of data. Images can be a type of data, text can be a type of data, acoustic or texture, whatever you call it. Now, to deal with multimodality, there are something called as VLMs, which is vision language models, right? Now, vision language models would mostly cater to images and text, but it is extendable to other type of data as well. There are different ways in which you can go about it. That is what I have listed here. But since this session is very focused towards demonstrating, I'll only go through contrastive learning. If you guys want to know about the rest of them, I can give you an appendix, or you can always reach out to me. But for now, we'll look at a particular way of achieving multimodality or neural search using contrastive learning, right? So, what is contrastive learning? If you go to the word meaning, contrast means a gradient between two different entities or two different pixels, let's say. Contrastive learning is trying to identify how different two entities are in terms of a similarity matrix. Let's say if I want to compare this chair with a chair next to it, how similar are they? But if I want to compare that chair with this one, how similar are they? So if you plot it in XY axis, I can really put these 2 points together, and if I measure their Euclidean distance, it will be really small. But if I measure the distance between those as an entity and this as an entity, it will be large. So what you are trying to do is, we have 2 types of encoder. One is a text encoder and one is an image encoder. Since the modalities are different, when you compare them, you have to get them to a higher dimension, which we call as hyperplane in machine learning terms, right? So you have to get them to a similar homogeneous space, which is also called as a latent space, where you can compare them. So that for that you need encoders. What is encoders? You take this image or you take this text data and convert it into embeddings, a basic vector, right? Now these vectors can be of n by n vectors, and then you can compare the distance between them. It's as simple as that, right? So what I'm doing here is taking the textual encoder, encoding them, and creating the vector here. Image, creating a vector here, and now I can pair them together. So let's say if I have a data like Apple's image and Apple is red in color, this is the text, then I can embed them both in a latent space and then put the pair together. That is the first step, that is contrastive pre-training that I do. Get the text, get the corpus of data, put them together in image and text pairs. What do I do after that? Create a dataset classifier from the labeled text. Now what you have is something very limited, right? Your corpus is not defining the entirety of the object that you're trying to define. So Apple is red in color, Apple can be green also. Slightly bright apple is something where you can call it yellowish also. So what you do is you create a classifier from the labeled text that you have, pass it on to the text encoder again, and then use it for zero shot prediction. What this will allow you to do is navigate through the multimodality of text and image together using the classes that you want to define. So let's say if you go and search that you want, just like we did, if you want coffee, you also get the coffee images, mugs or something like that, which are related to each other, but also get information about coffee. That's your textual corpus, right? So that was a more generic example. In geospatial context, what we intend to do is we have a query that a user comes with. That query can be a image, also a metadata. So this small file that you can see is the metadata. Now you have a database which is already trained, right? GeoFM is basically a fundamental foundational model for geoanalytics. You have trained these embeddings and you can take a query, you convert that into a embedding space or a vector, let's say. Then you compress them so that you can basically reduce the computations that is needed to compare them. And then you compute the distance between them. So let's say your database has some images, there is a query image and you compare the distance. So distance can be 5 to 7, whatever it is. The distance which is least is something that you would pick and retrieve to the user. So when I showed you the demo, what do you do is, if I put coffee, what it did is I had a whole catalog of the data that is available and it computed the distance between each of these products in the catalog. And the images that had least distance in terms of similarity is something that you saw in the screen. Sorry. Right. So I don't know if it's visible, but you can see that if I have a different orientation of aeroplane here and I put that as a query into my system, I would get a similar aeroplane. Now what you can possibly concur by this is there is a single aeroplane in space. So my dataset also gave a single aeroplane. There might be the dataset had multiple aeroplanes in the scene, but it chose to give me a single aeroplane because that was what I intended to get. So if my use case was to have a dataset in which I see only single aeroplane in the scene, I can use it. But if I try to get query aeroplane, I will never get a ship, basically, right? So if I'm going for maritime detection or something like that, I can put a simple ship image and get the data out of it. Similarly, if you look at textual context, I'll put jet, so associated images of jet will come. So textual to image translation. Ship, you will get ship images. So what exactly happens under the hood is what we are trying to explain here, right? The different shapes that you can see and the distances that you can see is because of the modalities of this data. So there is square means a different modality, circle means a different modality. You have a function which is your encoding, basically the encoders that we saw in the previous example. Then you create a joint embedding space which is your latent space, right? And then you try to find out the distance between them. So it can be intermodality, means between two different textual or image, or it can be intramodality, which means image to image or text to text. Both of these can be possible. And what basically it does is a simple matrix in which you put the most relatable or most similar elements in the diagonals, which is the most prominent one. And as and when it goes away from x1, so x1 is least related to y4, and y1 is least related to, let's say, x4. This matrix will help you to compute the positive, the negative, and what to ignore in your query. So we understood how the technology works, a basic understanding of how these deep learning models can be trained, what is the aspect of everything. So how do we deploy? There's just a basic deployment diagram in which there's this very, very high level understanding of how this needs to be developed. But to give a gist of it, you have a satellite which will transmit raw data to ground stations. From ground stations, you would take it to your cloud, and in cloud is where you process. Now, what you do is you have the metadata of the TIFF, let's say, you process it, and then you pass it to your embedding network. What this embedding network does is it creates a mapping of all the images that is there in this database, and then get the vectors out of it. So you get image vectors, metadata vectors, two different type of vectors. You put them into a vector database, right? A vector database is very specialized type of database, just like you have SQL or no SQL. There is vector database in which you can store these embeddings efficiently. The advantage that you can get is you can access this information much faster than traditional databases. These vectors may be very big in size. What I showed you as an example is very small. But when the complexity increases, let's say we are talking about 8, 16 or 32-bit bands, or 32 bands in optical, or different polarization in SAR, you would want to store them and access them faster. So vector databases are specialized databases for those. Now you have a database, you have a query coming in from the user, which is basically an image or metadata query. You do a vector search into your database and you find out the most relevant information out of it. And then there can be a console or there a dissemination platform where you will give it to the user. Now the user has the freedom to look for different options, access the data much faster, and then get the data set for training. So any machine learning use case that you see, the fundamental quality of the analytics would come from the quality of the data set, right? So you would want such kind of a system so that access to data is much easier and the quality of analytics that you do is much better. So I didn't put code in snippets or anything in this presentation so that it would have been difficult to comprehend the entire workflow in just a couple of minutes. So what I put is the technology that is available there. So I talked about vector search. So these are vector databases. VV8 is one type of vector database that you can use. Sorry. Doc arrays is one of the encoders that you can use. Now doc arrays can encode both images and textual and acoustic or whatever you want, different modalities of data. GenAI is a new orchestration tool that is open source. All of these are open source, by the way, that can orchestrate the entire workflow right from getting the embeddings to getting the relevant search. And there is Haystack by DeepSet, which is also open source. So what I would do is give you a gist of the code that we have developed for deploying such kind of systems as an open source basic model in the GitHub repository. If you would like to get back to me, to understand it better, or if you have new ideas, if you want to try out the data, or if you are in lack of proper understanding of how to go about it, you can always reach out to me at my email. And also, to make this possible, to make the data democratized to all the people, not only GIS, we are hiring, right? So we need people to make it possible. So if any one of you want to explore careers with Galaxy Space, please reach out to us. That would be it. Thank you. I will take questions. Yes.
Hi. So thank you for the presentation.
Mm-hmm.
So in one of the slides, you had shown how the search works. Like exactly
this one.
Let's say somebody is given a like an optical image of the aircraft, or maybe somebody has just written a jet and you've given an optical image of the aircraft.
Mm-hmm.
And you also mentioned that Galaxy has been working on hybrid imaging model.
Right.
In that case, what would the search written on like
like how would it decide on the relevancy for what kind of data I as a user want? Is it optical or is it a SAR data that I want?
Interesting question. So when you talk about hybrid data or fused data or co-registered data, we as a company would have access to both optical and SAR, which are temporally aligned. What I mean by temporally aligned is it's taken at a single instance of time. So when you want to search a particular object in terms of the entity that you want to train the model in, you can also explore the different sources. So you can only explore optical, only explore SAR, or you can even explore both of them fused together. That's a novel data set that we are offering. And the quality or the advantage that you would get is both of them would be registered. What I mean by registered is every pixel in SAR would be corresponding to every pixel in optical. So let's say if you are turning your machine learning model to go beyond optical images at some point, you would want the SAR pairs of it. So let's say if there is an image in optical shape, you don't want a SAR pair. Nothing in the world today gives you that kind of an access to data. Of course, there would be some satellites which have constellations and they would give you image pairs, but they are temporarily different. So that might induce some quality reduction in your analytics. But this is what we are trying to solve.
So if I'm searching for shape, I would get both the data.
Both the data, yes. And it would be on you to access which kind of data. And you can come back again to access the same search results for a different kind of data. Yeah.
Another question regarding the model. I don't know what is the extent of the model which you have mentioned, but I have a very simple question that rather than creating this whole system, why can't we have a single model or a multi-model which will help us creating the meta file, which will have the information about the image, what image has everything, and then have a simple text search engine which will just fetch me that meta file and then display the data. So why it is not done?
Right. So when you talk about metadata of a satellite image, you do not necessarily mean the image specifications of the data, right? Along with the image, there is platform specifications that come with it, right? So when I'm talking about satellite, I would necessarily want to know the look of the satellite. What is the swath width? What was the roll pitch yaw, let's say? What was the geometry? Positional vectors or velocity vectors of the satellite. Now, this is something you cannot differ from an image. This is telemetry information that we call in satellite terms. You would want to access that data also when you're training models. So let's say if you want to build a image reconstruction model, let's say, you would want access to this kind of information to train your model better. So this will be supplementary data to your latent space. So you have images, you get those encodings into your latent space. You provide this as a supplementary information to make the model fine-tuned according to your data. So that is why we cannot get metadata generated from the image. We also need an auxiliary or telemetry data along with it. So this is required.
Yeah, any more questions?
Any more questions? Yeah.
What kind of vectorizers are you using for text and image? Is it the same vectorizer like in a Siamese network, or are those two separate vectorizers?
Siamese networks wouldn't work for, as far as I know, it wouldn't work for multimodal. You have to make it a homogeneous data source. So if you're talking about image to image, Siamese can work. The vectorizers that you would use for text is basically something similar to tokenizers. So if you have heard of bag of words or embedding for textual information, or you can also use LLMs. If you have heard about transformers, right? They are encoders, decoders. You can use any encoder that is available out there, like BERT or something like that, to get these representations. The more complex data set that you use, architecture that you use, maybe you will get a very unique or nuanced vector. But that also means that your deployment scale is going up. So when I'm searching, I wouldn't want to wait for, let's say, 10 minutes to get the search results, right? So you have to get that combination right. And for image, it's simple CNN. You can get vision transformers out there also, a simple CNN also. You will get at the end is what you get an encoding. And encoding, the quality of the encoding is something that your use case determines. Yeah.
The search be available as a plugin tool for other spatial products.
Other spatial products.
Can I use the API with something from this to embed in other products? Just around spatial data.
Yes, you can do it. So that's the concept of it, right? When you're talking about multimodality, you can always increase the modality of your data, right? So if I'm today only restricted to GIS images and its metadata, if in future, let's say something interesting comes up like IoT sensors, right? If I'm able to get the IoT sensor data with me and map it with geospatial entity somehow, then maybe I can use both of them and make a fused source out of it and provide a richer analytics to my user. So that is also possible. Yes.
You talked about democratizing access to geospatial data for everyone.
Right.
So, is it possible for a local farmer in any small village to access the geospatial data?
If you implement this technology, which we are going to do, but if you do that, it's possible. So if I'm able to convert so a basic farmer would have an Android phone, right? So if I'm clicking pictures on ground, and if I'm able to transfer that into a GIS based entity, let's say if I'm able to understand the location or the nearby area of the farmer, so that is very much possible.
So you're developing this technology right now?
This technology that I talked about? No.
You're working on this?
We are working on neural search. We are going to deploy this kind of search-based access for our data sets also. And if you would like to get access to this data, you can always reach out to us. So we have been piloting on drones also, right? So we have data which is available for research. So if anyone of you want access to that, we can look through the applications as well.
So I would like to say one thing.
Yeah.
If I am not listening.
Yeah.
Basically, what I have seen is that the first seminar, whoever was the presenter, the first seminar, it was like Greek and Latin, right? The next seminar was like totally my emphasis is on like you could have combined the two seminars, focused more on going through the code and then inputting some images to see how it actually works. In other words, what I would like to say is that the third seminar, whatever it is presented by him, was like thoughtful, in a way that it was like more entertaining. The first seminar was like totally gone, right? The second seminar was like I wanted to see if this seminar focuses more on combining the theoretical with the practical way of actually inputting some images and then debugging that code, that collab to see, okay, where exactly it is, giving much more information. That I didn't see in this kind of seminar.
I mean, you wanted a demo kind of thing.
Demo. Most of the, I have attended C++ seminars, like given by Microsoft. What they do is that they go through that code. They actually see everything in real time, how it works. But this seminar was more on theoretical part. So I came to Microsoft Reactor with the hope that it will be of that kind of seminar. Right? I've attended MSDN seminars a lot of years back. Visual C++ seminars, C# seminars. The way they present the seminars and the way this seminar was presented was totally, different. I thought that way and came here.
I mean, you expected it to be a demo workshop kind of thing, but it turned out.
Then it becomes more interesting, like you input, because now if I have to input, you people are like subject matter experts, whereas I am not. So when I come to this seminar, when you combine the theory as well as with the collab notebook, the PyTorch notebook, or all that, and when you debug that, right, or run through the cells in by attaching it to a GPU instance or whatever, then I will know that, oh, okay, this is how it works, this is how the input images are, right. What if I increase the epochs from 10 to 20, what happens?
No. Your inputs is taken. I think we should focus more on practical side than on theoretical side.
Right. Then it becomes
understand. I mean, it's then non-GS audience also can understand.
Understand.
Yes.
Now it is all cricket Latin for me, right? Let's see.
No, hopefully we'll do that. What?
We also do workshops like here. This talk was mostly 3 speakers. Each has 30 minutes. In the 30 minutes, if they give demo also, even to set up it will take time. So we each do workshop, but then there will be only one talk. Yeah.
See, my emphasis is like something like, this is a Microsoft Reactor, right?
No. They has given us a space. So maybe if you give a credit or if you give, it's not good also, you give it to the structure because don't. They give us a space for us to organize the event. So other than that, Microsoft Reactor was
right.
It's not Microsoft. So even if it's not good, so you can blame on the structure. Don't blame on Microsoft Reactor.
It's not a question of blaming,
No, I'm saying even if
it's not a question of blaming. The point is like when people who are novices in this domain come to these kind of events, I'm sure in the second seminar that was explained, it's entirely cricket. Entirely cricket. It's all like matrix multiplication and all that. So that's okay, fine. I mean, right. For that you definitely have to be from mathematics domain, which I am also. So I could understand. But it's all what I've seen is that it is not that much entertaining. It's not that much educating.
We will maybe update in the next lesson. You can look out our page. So sometimes we do workshops also where the entire half day is focused on we give some problem like what you said. But only thing is when you call 3 speakers, everybody has just 30 minutes of time. That 30 minutes of time, sometimes even setting up your system to install the packages associated with that, your 30 minutes will be gone. So when we do workshops, we do as a whole day, like half a day workshop. So we will conduct some in the future.
I mean, maybe next time you people can focus on that more things.
Yes.
So that people like us can be, can learn something.
Sure.
Thanks. If anybody else has any feedback also.
Yeah. So thank you, Sumesh, for the presentation. So all these presentations from all 3 speakers will be available on GitHub, and we'll post it. I think in a day or 2. Alright. So with that, I think we conclude. Just before we close this, just want to make an announcement that if you guys want us to host at your place next time around, please do reach out. It could be related to geospatial, remote sensing, maps, or again AI. So anything of that sort, we are open to collaboration. Again, this event would not have been possible without IEEE GRSS. So IEEE GRSS Bangalore section is supporting us financially to conduct these kind of events. So hopefully in the next coming months also we'll be able to see all of you and with many questions. So with that, thank you so much. We'll now take a group picture, and then coffee, tea, snacks is available outside, so you guys can network. So thank you so much for coming. Hope you have a good day. Yeah, please everyone, please stand and come to the stage.